Here we are at Lakeside High School in beautiful Seattle. Now, look around you on this beautiful campus, okay? I'm going to make you a bet. This contains a lot more than hydrogen and helium. In fact, we can be pretty sure it contains a fair bit of carbon, oxygen, nitrogen, probably a fair bit of phosphorus, sulfur, and trace elements of all the other things in the periodic table.
The truly periodic table. The periodic table is this chart with a strange shape, with letters and numbers, neither a square nor a rectangle, with such a characteristic shape. Unmistakable. Some people know what each of these letters represent. C is the chemical symbol for carbon. O is the chemical symbol for oxygen. The chemical symbol for iron is Fe. Zn is zinc. There are even those who know the chemical symbol for sodium is Na, because it comes from the Latin natrium. Or that the chemical symbol for gold is Au, because in Latin it was called aurus. And also some know the meaning of the numbers that appear next to the letters, like for example the atomic number, which is the number of positive and negative charges of the atom. But what exactly is the periodic table? The periodic table is a chart that represents all 118 chemical elements that constitute the known universe. Everything around us is made up of at least one of these elements. 94 of these elements can be found in nature, and the rest were obtained in laboratories. 118 elements may seem too little for an entire universe, but it's not. Let's see. In stars like the Sun, 94% of all the atoms are hydrogen. The human body itself is very scarce on chemical elements. For every 100 kilos of weight, 65 kilos are oxygen atoms, 18 kilos are carbon atoms, and 10 kilos are hydrogen atoms, which leaves little room for all the other essential elements. Nitrogen, calcium, phosphorus, potassium, sulfur, chlorine, sodium, magnesium, iron, cobalt, copper, zinc, iodine, selenium, fluorine. The wonder of the chemical elements is that they combine with each other, and there's an almost infinite number of possible combinations that produce all the different chemical compounds needed to keep us alive and build everything around us. The water we drink, obtained by combining an oxygen atom and 2 hydrogen atoms. The glass we drink it from. The sugar in our coffee. The coffee. The cup and the metal of the little spoon we stir it with. The plastic our computer is made of. The rubber on the tires of our car and the gasoline that makes it run. Proteins. DNA. Everything around us and inside us are atoms that combined. An atom is the smallest recognized division of a chemical element and consists of a central core, with protons, positive charge, and neutrons, no charge. Surrounded by a cloud of electrons, negative charge. The properties of each chemical element are defined by the atom's nucleus and by the way electrons distribute in layers around it. These properties define the way atoms combine, or not really. Atoms react with each other through electrons of the last layer, the outermost layer. If the last layer has the same number of electrons, this means that the properties of these atoms are identical. The distribution of the elements in the lines and columns of the periodic table is not random, or just a question of design. The position of an element on the table tells us something about its chemical and material properties, and helps us to know and predict how two elements can combine. The periodic table organizes the elements from smallest to largest, according to its core and the distribution of electrons. In the first column of the table, we have the elements that have a single electron in the outer layer. And in the last column, we have those who have filled this layer. That's why each chemical element in the periodic table has a very well-defined neighborhood. Above and below it has elements with the same distribution of electrons and very similar properties. And on its right, it has an element that has an electron and one proton more, and therefore has different properties. We call it periodic because in this table, the elements become similar again periodically. Let's see, if we start at 3, lithium, the properties will vary regularly along the line until 10, neon. Here, the last layer of electrons gets full, and we move on to the next line and back to the first column. The properties of this element, 11, sodium, are again identical to the element that is directly above it, and so on. The tricky part is that the number of electrons filling one layer varies, and their distribution follows well-defined rules of quantum chemistry. 2 in the first, 8 in the second, 18 in the third, but in 2 phases. Which makes it necessary to distribute the chemical elements in the table in such a weird way. But in the end, everything makes sense, and we have the whole universe in a single table.
This is the periodic table. You can see all the elements we were just talking about. So here's the problem. There's hydrogen, there's helium. In a universe that had only hydrogen and helium, what could you make? Well, you certainly couldn't make all the stuff out there. You couldn't make a planet, you couldn't make a laptop, and you couldn't make my friend Raoul. Nor could you make my living friends over here. So this is a real problem. Where did all those other elements come from? And the answer is, they came from stars. So far, our stories have been about a universe that's cooling down. And that cooling down was really important because it allowed matter and energy to separate from each other, and it created the forms of matter that we've seen so far. But now we need to talk about ways in which the universe began to heat up. And that is something that happened inside stars. It was that heating up process that allowed stars to cook all the other elements that we've seen around us. And that's why stars are sort of the stars of this part of the story. The nearest star to us is our sun. At the surface, the sun is 5,800 degrees Celsius, but at its center, it's 15 million degrees. Now, think about that. Water boils at about 100 degrees Celsius. That's about 373 degrees above absolute zero, the coldest temperature there is. So the center of the sun is about 40,000 times hotter than boiling water. At these enormous temperatures, protons have a huge amount of energy. And as we saw in the last unit, they smash together really violently, and eventually they fuse to form helium nuclei. Now, that's pretty hard. But here's the problem. There's carbon up there. It's got 6 protons in the center. You can see the 6 above the carbon. So to get carbon, we need to smash 6 protons together. And for that, you need much higher temperatures, like 200 million degrees. And now let's go on to iron. Where's iron? There's iron. 26 protons. So now you need to smash 26 protons together to get iron. And to do that, you need temperatures as high as 3 billion degrees. So, Where in our young universe are you going to find temperatures of 3 billion degrees? The answer is inside dying stars.
Large stars have so much mass that they can create enormous pressures and temperatures. Those temperatures get cranked even higher when large stars run out of hydrogen. When that happens, fusion stops at the centre and the star collapses like a burst balloon. If the star's big enough, the collapse is huge, creating such high temperatures that helium nuclei can fuse into nuclei of carbon. When the star's used up its helium, it collapses again, and the cycle starts over. The star heats up and starts to fuse carbon to form oxygen. It collapses again, then does the same to create other elements like silicon, nitrogen, and eventually iron. If it's a really, really big star, it'll finally die in what's called a supernova. That's an explosion so hot and so energetic that, for a while, it'll shine like an entire galaxy, and it'll produce enough heat to form all the other elements of the periodic table. Then the supernova scatters these new elements into space, and voila! We have a universe with lots of different elements.
That's right, dying stars. And here's why. Remember that most stars spend most of their life, about 90% of their life, over billions of years, fusing protons, hydrogen nuclei, into helium nuclei. But think, what happens when they run out of fuel? Well, what happens is the furnace at the center of the star stops supporting the star, gravity takes over and collapses the whole thing. Now that collapse is really violent and it creates high temperatures at the center, but how high depends on how large the star is, how much stuff there is, how powerful gravity is. Now think of small stars. A small star doesn't have much pressure at the center, it burns hydrogen slowly over billions of years at low temperatures, and it lives a very long, slow life. And when it dies, eventually it runs out of fuel, it'll just slowly fade away, like a dying campfire. Nothing very interesting happens. Larger stars are much more interesting. They create higher temperature at their cores, they burn hydrogen much more violently, and when they run out of hydrogen and collapse, they generate much higher temperatures, up to 200 million degrees. Now you may remember, that's the temperature at which you can fuse 6 protons to form carbon. So they start burning helium to form carbon. Now, when stars run out of helium, things start moving faster and faster. When a star runs out of helium, it'll start fusing carbon into neon at close to 1 billion degrees. And then in a whole series of collapses and new fusion processes that get faster and faster and faster, it fuses neon into oxygen, then oxygen into silicon, and finally at 3 billion degrees, it fuses silicon into iron. And that's as far as the process can go. I'd like to read to you Cesare Emiliani's wonderful description of the final few million years in the life of a dying huge star. A star 25 times more massive than the Sun will exhaust the hydrogen in its core in a few million years, will burn helium for 500,000 years, and as the core continues to contract and the temperature continues to rise, will burn carbon for 600 years, oxygen for 6 months, and silicon for 1 day. By this time, the center of the star is like a sort of layer cake with all these different elements. And eventually, when it fills up with iron, it can't go any further. It'll collapse, it'll scatter its outer layers into space, and so they'll spread around the star into nearby space all the elements that it's just created. Well, that's great. Now we've seen how to generate all the elements in the periodic table up to iron. But what about all of these? Where do they come from? Well, the answer is the rest of these elements are produced not in dying stars, but in exploding stars. That's right, exploding stars. Now, when a really large star fills up with iron at its center, it eventually collapses and it explodes, generating staggering temperatures. These explosions are called supernovae, and they're amongst the most spectacular things you can see in the whole of astronomy. In just a few seconds, all the elements in the periodic table are manufactured in that supernova explosion. It shines so brightly, it generates such high temperatures that for a few weeks, a supernova can outshine an entire galaxy. In fact, many of the new stars that we hear about in history, such as the star over Bethlehem, may well have been supernovae. So now, where the dead star is, where the supernova was, we have a huge cloud of sort of dust and particles containing every single element in the periodic table, and it's drifting out into space. But let's put all of this in perspective. We began this unit, remember, in a universe that had just helium and hydrogen, nothing else. Now, at the end of this unit, we've got all the elements in the periodic table. But the truth is that even after billions of supernovae and billions of years, helium and hydrogen make up 98% of the atoms in the universe. All the rest makes up just 2%. So you may be thinking, what's the big deal about that? Well, that 2% is actually a huge deal. Without it, you couldn't make my friend Raoul over here, you couldn't make me, you couldn't make you. So it really makes a difference. And that's why in this course, we call the creation of new chemical elements the third great threshold of complexity. Hi, I'm back at Lakeside School, and I'm in the chemistry lab, as you can see. Now, look around you and try and count how many different sorts of materials you can see. 10 easily, 100, not too hard. And if you counted really carefully, well, look at all these materials here. You could probably come up quite easily to 1,000, 10,000, or maybe even 100,000. That's because in a universe with 100 elements, you haven't just got 100 different materials. Those elements can combine with each other in a huge number of different ways to form millions and millions of new materials, all the materials we see in the world around us. All these new materials eventually combine to create entirely new astronomical bodies. The most important by far for us, of course, is our home planet, the Earth. But before we describe how the Earth and the other planets of the solar system was created, there's a little problem we have to take up. You'll remember from the last unit, we saw that all those new elements that were created made up only 2% of all the atoms in the universe. Yet if we look at our Earth, we'll find that 90% of the Earth is made up of elements like iron, oxygen, silicon, magnesium, and other elements created in supernovae and dying stars. So how did they get concentrated like this to form planets and bodies like that? Now, before I give my answer, I'd like to ask if you have any ideas about how that might have happened. To answer these questions, we must think about chemistry. Now, chemistry is all about how different elements link up, how their atoms link up to form what we call molecules. How atoms link up depends very much on the arrangement of their electrons. Some elements, such as helium, are very, very stable. They hardly ever link up with other atoms. In fact, they're known as the noble gases. It's as if they're too snooty to join up with other atoms. You'll find them on the right side of the periodic table, by the way. But most atoms really like to link up with other atoms. We say they're reactive. Hydrogen and oxygen, for example, are always looking for chances to link up with other atoms. If you see burning or you see a flame, what you're really seeing is oxygen linking up really violently with other atoms. It's very reactive indeed. Now, when atoms join together, we call them molecules. Each molecule has its own distinctive qualities, which may be very different from the elements of which they're formed. For example, hydrogen and oxygen are both gases, but when they combine, they form a very, very familiar liquid, water, H2O. And water has qualities completely different from both hydrogen and oxygen. Different types of molecules also have different types of bonds. Some bonds are extremely rigid, but others are very flexible. Some are very strong, very hard to break. Others are very easy to break. So there's a huge variety of different types of links between molecules. Carbon, for example, can link up with itself to form diamonds. Now, in a diamond, the bonds are extremely strong and extremely rigid, so a diamond is very tough indeed. But carbon atoms could also link up with themselves to form a very different material, graphite. Now, graphite is the lead in a pencil. It's very soft stuff indeed. So different bonds make a lot of difference. Now, these different types of links, different types of bonds, mean we have a huge variety of different types of materials. That's what explains the huge variety of these materials. But note that it's mostly elements other than hydrogen or helium that make up these chemicals. And that's one reason why when we talk about rich chemistry, we're talking mostly about that tiny 2% of elements from the periodic table. Atoms began to form molecules even in deep space, in the clouds of matter ejected by supernovae and dying stars. How do we know this? Well, using spectroscopes, we can tell what elements and what chemicals are out there. And we know there's water, plenty of ice, carbon dioxide, ammonia, acetic acid, a whole range of simple molecules that are very familiar in daily life. There are also lots of silicates. Silicates are molecules made from silicon and oxygen, and they make up most of the rocks in the Earth's crust. Now in space, these molecules, which were pretty simple by the way, they included 10 to 20 atoms, at most 60. In space, these molecules couldn't do a huge amount of interesting stuff. But around newly born stars, it turns out you could do a huge amount of interesting stuff with these molecules. In fact, you could make planets. To see how this works, what we're going to do is we're going to travel back in time 4.5 billion years, and we're going to zoom in. We've been looking at the universe so far in this course. We're going to zoom in on one rather average galaxy, the Milky Way. We're going to zoom in on one tiny part of it, and we're going to look at the birth of our solar system. Now, our sun formed like any other star from the collapse of a cloud of matter under the pressure of gravity. That collapse, like many others, was probably triggered by a huge supernova explosion somewhere in our region of the Milky Way. And that supernova explosion also seeded this cloud with lots of new materials from other supernovae and from dying stars. As the cloud collapsed, it began to spin, like a spinning pizza dough. And as it spun, it slowly flattened out to form a disk. Now, this is something that happens throughout the universe, which is why the universe is full of flat disks, from the Milky Way itself to our solar system, even to the rings around Saturn. Astronomers call this sort of disk a protoplanetary disk, or a proplid. Now, as the proplid that eventually formed our solar system began to collapse, at its center it got hotter and hotter and hotter until eventually fusion began and our sun was born. About 99% of all the material in the proplid went into the sun. 99.9% in fact. That leaves 0.1% for the rest of the solar system. All that stuff was orbiting around the sun, and amazingly that tiny residue is what formed all the rest of the solar system. Now let's begin by looking at the outer gassy planets and how they were formed. The intense heat of the young sun drove away gassy materials from the inner parts of the solar system, and above all, it drove away a lot of hydrogen and helium, leaving that as a region deprived of hydrogen and helium. And all that gassy material gathered further out in the solar system and eventually condensed to form the gassy giants. They are Jupiter, Saturn, Uranus, and Neptune. Now, they contained about 99% of the leftovers. So what we're left with is a tiny residue of a tiny residue to form the inner rocky planets, including our Earth. Closer to the Sun, from that tiny residue of a residue, you find material orbiting in the inner orbits. And that material is less gassy, there's more sort of solid stuff. You have little dust motes that eventually will gather together through electrostatic forces or collisions to form little rocks. You have particles of ice that will eventually form snowball-like objects, and then eventually they form things like meteorites or asteroids, and they're getting bigger and bigger and bigger, and they're colliding with each other. And in each orbit, you eventually get large objects that finally sweep up through their gravitational pull everything else that's in the orbit. And so eventually, over 100 million years, in each orbit, you have a rocky planet. Now this process is called accretion. It's extremely violent. There's a huge amount of space stuff smashing into other space stuff. And if you want to be persuaded how violent it was, get out a pair of binoculars and look at the moon one night and look at those craters. Those are evidence of how violent the process of accretion was. Our moon was probably created when an object, perhaps the size of Mars, collided with our Earth, our young Earth, and it gouged out a huge chunk of the Earth. And that stuff orbited around the Earth and slowly accreted to form the object that we call the moon. So in this way, through these processes, over about 10 to 20 million years, our solar system formed. And we end up with a solar system that has inner rocky planets in the inner orbits, these large gassy planets in the outer orbits, and woven through them lots of space debris. It includes meteorites, asteroids, and comets. No one knew if there were any other solar systems anywhere else in the universe. It was quite possible this was the only solar system in the universe. But in the last 15 years, there's been some quite magical astronomical research, a lot of it based on satellite telescopes, such as the Kepler satellite. And what we now are able to do is actually see other solar systems. They vary hugely. But we now know that solar systems are actually very, very common indeed. And strangely, what that does is it rather increases the chances that out there somewhere there is life of some form. So exciting is the science, by the way, that I even have an app on my phone that tells me all about the most recent discoveries of so-called exoplanets, which is what planets around other stars are called. Let's return to the problem we began with in this unit. How is it possible from all these rare new chemical elements to create entirely new things? And I hope by now we have the beginnings of an answer. First, we saw that chemistry links chemicals to form simple molecules, a whole range of new materials. They're floating through space. And secondly, we saw that in the environments, and we can call them the Goldilocks environments, around newly formed stars, those molecules get smashed together. They get brought together by chemistry and by gravity and by electricity to form objects like dust motes, meteorites, asteroids, and eventually planets and solar systems. Now, we regard the creation of solar systems as the fourth great threshold in this course. And that's because planets, and in particular rocky planets like our Earth, are significantly more complex than stars. They are more complex because they have more internal structure, but they are also much more complex chemically. They contain a much greater diversity of materials. Okay, now I've worn this lab coat throughout the whole lecture, even though I'm a historian. I think it's time to take it off. But I hope you're beginning to see that what's happening is that our universe is getting more complex, more diverse, and more interesting. Imagine you're in a time machine and you've traveled back 4.5 billion years. And what you're doing is you're taking a stroll on the early Earth. Now, what would it be like? And would you be having fun? Well, the answer is, I don't think you'd be having much fun. First, you'd be walking on molten lava.
Ow.
Not nice. Secondly, you couldn't breathe because there's no oxygen. You'd be asphyxiating. And thirdly, you'd be ducking asteroids and meteorites that are crashing into the early Earth, lots and lots of them. And fourth, you'd probably be throwing up because of very high levels of radiation. And if you stayed there too long, your hair would start falling out too. So I don't think you want to stay there too long. Why was the early Earth so hot? Because that's the main thing, it was really, really hot. Now you've already got some clues as to why it was so hot. And you might be able to think this through. But let me give you 3 of the main reasons. First, do you remember that supernova that blew up just before the solar system was formed, that created huge amounts of radioactive material. And that radioactivity generated a lot of heat. Today, a lot of it's dissipated. So today's Earth is nothing like as radioactive as it was 4.5 billion years ago. Secondly, you remember the process of accretion, really violent, lots of space debris crashing into other space debris. Each collision with a meteorite or an asteroid created huge amounts of heat. And the third problem is subtler because it's pressure. You remember those clouds that the early stars formed from? Well, as the clouds got denser, you remember the pressure increased and they got hotter. And the same thing happens with the early Earth. As it accreted, it got larger, pressure built up and heat built up, particularly at the center. So that's why the early Earth was so hot. In fact, the early Earth got so hot, it melted. And that is really important, because if it hadn't melted, today's Earth would be very different from the way it was. To get a sense of what happened and why this was so important, let's imagine a kind of absurd experiment. Okay, so you're going to put some stuff in a saucepan. You're going to put in some coins. You're going to put in some rice. You're going to put in some plastic. Let's add a bit of mud. Let's put in some ice, and then you can chuck in one or two other things. And now we're going to heat that stuff up to several thousand degrees. Don't stir, just let it simmer. Now, it's not going to taste good, but we may be able to learn something from this. And what we'll see is that the whole thing's going to melt. The heavy stuff, such as the coins, are going to sink down to the bottom. Lighter stuff is going to rise to the top, and some stuff is going to evaporate and boil above the saucepan. Now, something very like this seems to have happened to the early Earth. It melted, and because it melted, it formed a series of layers, and they give it its structure today. Let's look at the four main layers. Now, the first is at the center. It's the core. It's metallic. Nickel and iron, above all iron, sank to the center of the Earth. And the fact that the center of the Earth is full of metal is really important, because this gave the Earth its magnetic field, and the magnetic field deflects some of the sun's rays that would be harmful to living creatures such as us. So that's the first layer, the core. Secondly, lighter stuff, lighter rocks float above the core and form a layer that's called the mantle. Now, the mantle you can think of as a sort of hot sludge of rocks. These rocks are so hot, they're sort of semi-molten, and they're actually moving around in convection currents inside the mantle. And then at the very top, you have a layer called the crust. Very light rocks, such as basalts and granites, reach the top, they cool, they form this thin layer, the crust. That's where we live. But the crust is pushed around by those convection currents from underneath. You can think of the crust as a tiny thin layer, a bit like a sort of eggshell. And finally, the fourth layer, the atmosphere. Some of the gassy stuff bubbles up to the top, it evaporates. The very light gases, such as hydrogen, disperse into space. But a lot of other gases just hang around the Earth, held by its gravitational pull. And that's how the Earth acquired the structure it has today. All of this happened about 10 million years after the creation of our solar system. Now I want you to hop back in that time machine. And what I want you to do is to take off from your backyard and hover over your hometown. And now I want you to put the time machine into fast motion, so it's moving rapidly back through time. And you're going to see something really weird. What you're going to see is that the land is going to start buckling and shaking and moving like a huge monster. This looks weird to us simply because we don't live long enough to see that the Earth is in fact changing all the time. Now, in fact, some scholars began to notice this as early as the 16th century when they studied the first world maps that were ever produced. Some of them noticed odd things, like the fact that West Africa seems to fit well into Brazil. I mean, look at a modern map and you'll see the same thing. In the early 20th century, a German meteorologist called Alfred Wegener found lots of evidence to suggest that the continents had in fact once been connected. For example, he found very similar geological strata in West Africa and in Brazil. And during World War I, he wrote a book arguing that once all the continents on Earth had been united in a single supercontinent that he called Pangaea, after the Greek goddess Gaia for the Earth. Now, what did the other geologists think of this great idea? They were not impressed. Here's the problem. Wegener came up with heaps of evidence to show that the continents seemed once to have been linked. What he couldn't do was explain how the continents moved around the Earth. So when they said, okay, Alfred, how do you tow a whole continent around the Earth? He couldn't explain it. And as a result of that, his great idea was ignored for almost 40 years. We saw when looking at astronomy that quite often new technologies can generate new evidence which changes our understanding of the science. And something very like this happened in geology. During World War II, sonar technologies were developed to track submarines. And after World War II, some geologists used that technology to try to map the ocean floor. And when they started doing this, they found something that really surprised them. Through many of the Earth's oceans, they found huge chains of volcanoes. And what's happening is that lava is coming up from the mantle, it's rising up, it's forming mountains, and it's pushing apart the old oceanic crust. In the center of the Atlantic Ocean, for example, there's a huge chain of these mountains, and what they're doing is they're pushing the Atlantic apart. So the Atlantic is actually getting wider and wider at about the speed that your fingernails grow. Now, some geologists thought, okay, does this mean that the Earth as a whole is just getting bigger and bigger and bigger like an inflating balloon? But they soon realized that elsewhere in the Earth, crust was going back into the mantle, which balanced what was happening in the Atlantic. Let me explain how it works. Now, to understand this, you need to think of two basic types of crust. There's continental crust, which is the land that we walk on, and then there's oceanic crust, the land beneath the oceans. In general, continental crust is lighter. It tends to be made of granites. Oceanic crust tends to be heavier, made of basalts. Okay? Now, once you've got that, think of two bits of crust colliding, continental and oceanic. What's going to happen? Well, what's going to happen is that the heavier oceanic crust is going to dive beneath the continental crust. Now think of this. It's grinding against the continental crust. It's creating huge friction and lots of heat, and it melts part of the continental crust and punches up whole mountain chains. And that basically is how the Andes mountain chain was formed. Mountains can also form when portions of continental crust collide with each other, but this time, because both portions have about the same density, they don't dive beneath each other, but they crumple up to form huge mountain chains. And that's basically how the Himalayas were formed about 50 million years ago, when India crashed into the mainland of Asia. Now, there's another type of relationship between different parts of crust. Sometimes you get two bits of crust that are moving in opposite directions past each other. What happens is that the friction holds them, but the pressure builds up and then suddenly they slip. This is what's happening along the San Andreas Fault in California, and it's that slippage that creates earthquakes. Okay, these are the basic ideas of the modern theory of plate tectonics. And the theory of plate tectonics is the fundamental idea of modern geology and earth sciences, just as Big Bang cosmology is the fundamental idea of modern astronomy. It explains a huge amount about how the Earth works, just as Big Bang cosmology explains how the universe works. It explains, for example, why all around the Pacific you get a ring of volcanoes and earthquakes. It explains why the Earth is broken up into a series of plates, like a broken eggshell, and why it's around the edge of those plates that you get violent activity such as volcanoes and earthquakes. It explains how mountains form. It explains all the fundamental features of our Earth, and also how the continents move. It explains what Wegener couldn't explain. So the theory of plate tectonics is now the most fundamental idea in modern earth sciences.